Oh, can you hear me? Okay, it's okay. So, as I announced on the Blackboard, so the next class will be canceled because I need to attend the workshop. It's the ITIC workshop. So I need to cancel the next class. I'm sorry about that. But I will record the lecture video and then I will post the lecture video also on YouTube, like the other lectures. So please watch the recorded YouTube lecture. Also I posted the lecture video on the YouTube on maybe the Saturday night. So okay. So actually in the recorded lecture, so I explained about the pipelining, and then I said that the pipelining is it's a very important concept we need to learn in this course, right? So okay. So I hope the PA can bring the battery for this mic. Okay, so the pipelining. So actually, I explained that in the single cycle process architecture, the problem is that the delay of the data pass. So we need to accumulate the delay of each data pass element, and then the problem is that the delay is so long, and then so I said that the clock period needs to be larger than larger or greater than the sum of all combinational delay. So in the single cycle processor, because the delay of the combinational logic is so long, so we need to set the long clock period. And then so we learned in the chapter 1 the execution time. The execution time of a computer system is actually proportional to the clock period. So which means that if the clock period is long, then the performance is low. Okay, so that's why. So we need to apply pipelining. So what is the pipelining? So in the lecture video, in the posted lecture video, I showed this analogy. So this is the it's similar to the single cycle processor. So all required tasks need to be performed within one clock period. So this is the similar to the single cycle processor, and then this is the analogy of pipelining. So what is the pipelining? So we just split the steps. What tasks for? So actually, we just split the required steps for executing instructions, right? So in the pipeline architecture, we divide the pipeline stages into 5 stages, right? So these are required steps for executing instructions, but we just split these steps, what is tasks, and then for each clock, each stage is performed. Okay. So for example, when an instruction is executed for the first clock, then the instruction fetch of this instruction is performed. And then in the next clock, the id stage is performed. But at the same clock slot, at the same clock cycle slot, the next instruction can be in the instruction fetch stage, right? So like this figure. So in the second slot, second time slot. So actually, different steps are performed for the different tasks, right? So this is the pipeline. So What is the benefit? So I mentioned that when I explained about the pipelining. In the first clock, then instruction fetch is performed. And then in the next clock, the next stage, the next step, ID step will be performed. Okay, so we can split the steps for executing instructions into 5 steps or 5 stages, like instruction fetch, ID, execution, memory, and write back. And then we just assign a single clock cycle for each step. Okay, so one clock cycle for instruction fetch, and then another clock cycle for instruction decoding, and the next clock cycle execution, and then memory and write back. So what's the benefit? Actually, in a single cycle processor, then the sum of delays of all steps is the critical delay. Okay, critical delay of a single cycle processor. But in the pipeline processor, actually the longest delay is the delay in each step, right? So that's why I explained in this table. So we can reduce clock period. So if we can reduce the clock period, so which means that we can reduce the execution time. Okay. Also in the pipelining, so actually the processor receives instructions every clock, right? Like the single cycle processor. For the single cycle processor, this single cycle processor can receive each instruction at every clock, right? And it's the same for the pipeline processor, right? So in the pipeline processor, the instructions are also given to the processors at every clock cycle. Okay. And then in the first video, so I explained about the hazard. So what are hazards? What is the definition? So hazard looks like this. Actually, this is the normal meaning of the hazard. So like it's a kind of flat ground, so we can find a hole or some crack. And then these holes or cracks are called hazards. Okay, so like on the flat ground, we can find some holes or some obstacles, cracks. Then those are called hazards. Actually, in the real world, in the normal world, but in the pipeline architecture, so you need to understand the meaning, the definition of the hazard. So hazard is that the instructions cannot be executed in the next cycle. Okay, so which means that clock cycles are wasted because the instructions cannot be executed. So you can understand that the hazards are events that waste clock cycles in the pipeline processor. Okay, so clock cycles are wasted, then you can understand that, oh, these are hazards. Okay, and then there are 3 kinds of hazards. So it's a very important: structure hazard, data hazard, and then control hazard. And we classify these hazards based on the reasons of the clock waste event. Okay, so which means that what are structure hazards? So clock cycles are wasted because of lack of hardware resources. Then this event called a structure hazard, right? The data hazard, the clock cycles is wasted because of data dependencies, and then this is called a data hazard. Okay. So if you watch it posted video, then you can find some the examples of a hazard. Actually, the structure hazard is actually we cannot observe structure hazard in the pipeline process. So actually, this RISC-V single cycle or pipeline processor, right? Because we divide the memory into instruction memory and data memory, right? So structure hazards are not observed in the pipeline processor, but we can observe data hazard, right? So it is because so normally when the data is written back to the register file, it is performed in the last stage. It's a write back stage, right? But this data, the data is demanded in the ID stage. So register is read in the ID stage. So you can find some time gap between the write back and ID stage. So we can observe a data hazard, but in order to avoid a data hazard, so we can forward the data into some input of ALU, right? So this is the data hazard. Okay, so and then but I also mentioned that if the former instruction is a load instruction, then we cannot avoid data hazard with data forwarding, right? Because the result is generated at the end of memory stage, right? But if the next instruction is here, then the next instruction requires the operand at the start point of the execution stage. So here, so data is demanded at this point, it's a demanded, but data is generated at this point, it's a generated. Okay, so if you just see the time, if we just compare the time between the generated time and then demanded time, then you can find that this is the future and then this is past. It's not possible, right? So the data cannot be forwarded. So in this case, the next instruction needs to be delayed by 1 clock. Okay, so which means that if the next instruction is delayed, then the execution stage of the sub instruction is here. So this generated data can be forwarded to this point, at the start input port of the ALU. So this is the future and this is the past. So it's possible. So data can be delivered. Okay, it's a forwarding. So actually, if the former instruction is a load instruction, we cannot avoid data hazard. So I also explained about some optimization technique by compilers, right? So compilers can change the order of instructions in actually within the basic block. Okay, so as you can see, this is the basic block, right? So there is no target of branch inside of this block. So there is no branch instruction. So inside of this block, right? So compilers can adjust some orders of instructions inside of the basic block. So, but we need to also keep some data dependencies, right? So so we cannot change the order like the A equal B plus C and then D equal A plus 1, because A needs to be generated by this statement, and then the result of this former statement is used by next statement. So we cannot change the order of these dependent instructions, right? But if the instructions are not dependent each other, right, then we can change the orders. So compilers can also change some orders of instruction, then we can avoid the data hazard, okay, in this case. Okay, so now, I will explain about control hazard. So I mentioned that in the previous class, the recorded video. So I mentioned that the control hazards are caused by control instructions such as branch, jumps, and exceptions. Okay, so we will learn about exceptions in the later. So, but you can understand that if the program counter of the next instruction is updated, then the control hazard can be caused. So control hazard can be observed. Okay, why? So you can. I will explain with an example. So you can find this example here. This is the add instruction here, and then this is the BQ instruction, right? So for the add instruction, this is the instruction fetch, it's ID, execution, and write back. And then, so this is the BQ instruction. So this is the clock cycle 1, 2, 3, 4, 5, 6. So at the clock cycle number 2, then BQ is fetched. It's an instruction fetch, right? Then what's the next instruction? So next instruction should be OR instruction. So at clock cycle number 3, so this slot, the OR instruction needs to be fetched. So what's the problem? We don't know. We don't know the next program counter if the current instruction is branch instruction, right? Why? Because the condition of this branch instruction, the next instruction, the next PC, next PC can be PC plus 4, it's a false case, right? And or PC plus immediate, it's the true case. So there are two possible cases, but in the single cycle processor design, the branch instruction, the result of a branch instruction is computed by adder, but in order to compute the, the result of a branch instruction is computed by ALU, right? So ALU, right? Then where is the ALU? The ALU is computed in this execution stage, right? So actually, the branch instruction, the result of a branch instruction is calculated by ALU here, and then the result is determined at this point. But in order to fetch the next instruction needs to be fetched at clock cycle 3. So what's the problem? We don't know the next PC because the condition of a branch is not resolved. So we need to wait until the end of clock cycle 4. Okay, because the branch is the PQ, so we need to use the ALU, but ALU computation is performed in the execution stage, right? So that's the problem. So what actually when the instructions are executed, even though we don't know the result of a branch instruction, but actually this is the normal case, right? So normal case means that if the current instruction is the normal instruction, it's not a branch instruction, then usually we just, the next PC is the PC plus 4. Okay, so when the branch instruction is executed, so even though we don't know the next PC, but we assume that the next PC is the PC plus 4. And if the branch is true, the branch condition is true, then we cancel the executed instructions in the pipeline. So anyway, so if we cancel the execution of some stages like this, then clock cycles are wasted because some pipelining stages include a certain steps of instructions, right? The clock cycles are used, the clock cycles are taken, but these instructions are canceled. So canceled from this pipelined stages. So which means that these clocks, so clocks occupied by these canceled instructions are wasted. Okay, do you understand? So clock cycles are wasted because of control instructions, branch instruction. Then this wasted event, the clock cycle, if the events that clock cycles are wasted, so this event is called a control hazard. Okay, so which means clock cycles can be also wasted by branch instructions. Okay, so that's actually, so in order to avoid, so you cannot avoid actually, but this branch it's a control hazard, but we can reduce the influences from control instructions using the prediction. So we will learn about the branch prediction later. Okay, so but we need to understand. So clock cycles can be wasted because of lack of hardware resources, the structure hazard, and then data dependency, the data hazard, and then branch instruction, control hazard. There are 3 kinds of hazards. Why? But then we need to learn? Why we need to learn about hazard? Because it is critical for the performance. Okay? So think about this execution. Okay? So this is very important execution, right? Because I use this equation very frequently, right? So execution time is instruction count, CPI, and PC. And then actually the instruction count is determined by software, right? And then compiler. Okay, so this is the software part actually. The hardware or hardware architecture decides CPI and PC. And then using the pipelining, we can reduce TC, right? We can reduce TC using the pipeline architecture. But CPI, the clocks per instruction can be increased by hazard, right? So if the clock cycles are wasted, then CPI will be increased. So execution time will be increased. So hazards are critical for the performance of processors. So it means we need to reduce hazard in the processor architecture. That's why we learned about the hazard. Okay. Okay, so now I will explain how to design pipelined architecture or pipelined processor. Okay. So we can start from the single cycle processor. So it is because the single cycle processor is the complete processor design, right? So single cycle processor also includes all required steps for executing instructions. And then in the pipeline architecture, I mentioned that in the pipeline architecture, we just divide these steps into the multiple pipelining stages, right? So which means we can start from the single cycle processor. So this is actually the full, this figure shows the full data path of a single cycle processor, right? Right? So, and then we can divide some steps of a single cycle processor into 5 steps. This is the instruction fetch, and this is ID, instruction decoding. 감사합니다. Okay. So, so this is the ID stage, and this is EX stage, and this is the memory, and then it's the write back. So actually, the in the write back stage, the result is written back. The result is written to the register file, right? So actually, you can find this is the result. The result is written back to the register file. So this is the single cycle processor, and then we can just split up some steps of single cycle processor into 5 parts, right? 5 parts. And then how can we implement pipelined processor? So firstly, we need to use the pipeline register. So actually, this is called a register, but actually, this is the group of the flip-flops. Okay, so you need to understand. So these registers are not kind of architectural registers. Okay, so we can store some data in these registers, the pipeline registers, but these registers are not architectural registers, such as the integer registers or floating point registers or program counter. So actually, these registers are defined by ISA, instruction set architecture, but pipeline registers are not defined by ISA. This is the microarchitecture area, okay? And then you need to understand. So you need to understand that pipeline registers are actually groups of D flip-flops. So I already explained about the D flip-flops, right? So when we implement digital system, so this is these are D flip-flops, and then same clock signal is connected to the clock port of D flip-flops, and then between these 2 D flip-flops, we can find combinational logic. So we can understand the pipeline architecture design like this figure. Okay. Okay. So in this figure, so we can observe several pipeline registers. So several pipelining flip-flops. Okay. So this is the instruction fetch, and then instruction decoding is execution, memory, and write back. And then I said that these are actually flip-flops. So same clock signal is connected. So we can, the same clock signal is connected like this. So it's the clock. So what does that mean? This is the clock signal, right? So, and then, this is the clock period. So at the rising edge of the clock, the input signal the PC is also the clock is connected. So at the rising edge of the clock, the input signals are given to the combinational logic or data path element, the pipeline, in a pipelining stage. So for example, so you can find the so actually, and as also we use the slash like the instruction fetch slash ID. So this represents the pipeline register between instruction fetch and ID stages. Okay, you can find the slash here, the ID slash EX and EX slash ME. So if we just focus on the ID stage is here, okay? So at the rising edge of the clock, so I said that this is the flip-flop, right? So at the rising edge of the clock, these signals are initiated. So as you can see, the instruction from the instruction memory is given to the instruction fetch and ID pipeline register. So at the rising edge of the clock, this instruction signal, so it's also signal or instruction data. This signal is sampled by clock signal, rising edge of clock. Okay. So rising edge of the clock, right? And so this is the clock signal here. So the sampled data, sampled instruction here in this example. So this data is given to the ID stage. Okay, you can find some data path here. Right? So instruction is here. So this sampled instruction data is given at the rising edge of clock. And then it is given to the register, to the data path element. Okay, so and then you can find some result like the read data 1, read data 2, and immediate data. Okay, so and then also in the next clock edge, the rising edge, at the next rising edge, these results, okay, these results are also sampled by this clock signal, and then sampled in the ID slash EX pipeline register, right? So these are sampled, and then also sampled data is given to this path. Okay, so do you understand? So that's why I mentioned this model. So in this model, so this is the combination of the logic, and you can also these are combinational logic. So data path elements are actually combinational logic. So and then in the rising edge of the clock by this flip-flop, the input of this combinational logic is sampled and then delivered by this flip-flop, right? It's the same, right? By the instruction fetch and ID pipeline register, which is flip-flop. At the rising edge of the clock, so this instruction, so that is the result of instruction fetch stage. This result data is sampled and then delivered to the next stage, the ID stage. So synchronized, and then it's processed by, so those data are processed by data path elements in the ID stage. Okay, and then result. So generated results are sampled at the rising edge of next clock. So at the sampled by is flip-flop. Okay. sampled by this flip-flop. Okay, so we can understand the pipeline architecture like this. So actually, between stages, we just insert pipeline registers or group of big flip-flops, and signals are sampled at the rising edge of the clock. Then the sampled data is delivered to the next stage. Okay, this is the operation of pipeline processor. Okay, so you need to understand this. So actually, this is the very important concept. So I hope everyone can understand this behavior of pipeline processor. Okay. So if you can understand this, then I believe you can understand the some behavior of pipeline processor. Okay, so then let's see the some detailed operations in the pipeline processor. So this is the instruction fetch stage. Then this is the load word instruction. So actually, in the previous edition, we just studied the 64-bit computer. So actually, the load instructions are words word LD. But now, so we are learning about the 32-bit computer system. So actually, this is the load word. So in the instruction fetch stage, so I mentioned that the clock signal is also connected to the clock port of PC register. It's a program counter register. So which means this is the clock signal. Okay. So at the right, just after the rising edge of this clock, then PC is generated by PC register, the program counter, because this is also very similar to the flip-flop. So PC is generated at this point, just after the rising clock edge. Okay, so PC is generated, and then as you can see, the PC is connected to the program counter value, is connected to the address of instruction memory, and also you can find this is also PC, this is PC. So, and then this is 4, okay, which means this is the PC plus 4. Okay, and then and the PC is given to the instruction memory, then we can get instructions. Okay, so at the later part of clock signal, like around here, and then we can get these results at the PC plus 4, and then so PC is also here, the PC and the instruction. Okay, and then the PC plus 4 is given to this multiplexer, because this instruction can be a branch instruction. So the next PC can be PC plus 4 or PC immediate. So we need to actually make some data pass for the branch instruction here. So PC plus 4 is also given to the program counter for the next instruction. And as you can see, PC is given to the instruction fetch and ID pipeline register. So this is the flip-flop, right? And inst is also given to the instruction fetch and ID pipeline register. So at the rising edge of this clock, the next rising edge, this PC and inst are sampled. Okay, And then the next clock, this is the ID stage. Also, we can find some clock signal here. So PC, so sampled PC and sampled instruction are delivered to the ID stage at this timing. So just at the rising edge of clock. So these data, these PC and instruction data are given to data path element like register file and immediate generator. Then we can get several data. Actually, the PC we do nothing for the PC. And then so we can get read data one, so RS1 data, and then RS2 data here, then immediate data here. So at this timing, so we can get the result from data path elements like the register file and immediate generator at this timing. And these data are also sampled at the rising edge of the clock. So this is the execution stage. Execution stage is here, and then so sampled data are also delivered to the EX stage, and then so these data are also processed by ALU, because there are some adder for the branch instruction. And then we can get result here. Then the memory stage, then with the generated signals, so we can access data memory. Okay, and then we can get the address here, like here. And then in the write back stage, this is the load word. This is the write back stage. Then result will be written back to the register file. Okay, that was the problem. So, but when we design pipeline architecture, then we need to consider the timing of signals. So this is actually very important, very critical. So what's the problem? So I mentioned that. So this is the write back stage. And then, so which means that the result will be written back to the write data port of register file. But what's the problem? Problem is that actually the load word is in write back stage. So which means that in order to store data, then we require data and RD. Right. So the generated data is stored to the register file indexed by RD. So which means that in order to store data, then we also require RD. So as you can see, the data is written back. The data is delivered to the write data port of register file. So data is this data is the data of load word. Okay, right? This is the data of load word, because load word is in write back stage. But how about the RD? So if you see the write register port here, so it's small actually. So if you see the write register port here, then you can find that, oh, this instruction is connected to actually the part of instruction. the instruction is connected to the right register port of the register file, but this instruction comes from instruction fetch and ID pipeline register. Oh. What's the problem? The problem is, so data is the data of load word in write back stage. But in this figure, RD is the, we don't know the instruction, but the RD is the RD of the instruction in ID stage. Do you understand? So which means that the RD is incorrect number, okay, incorrect register number, because the in this figure the ID is the ID of the instruction in ID stage. But where is the load word? Load word is in write back stage. And then you know, in the pipeline architecture, different instructions are in the different stages. Okay, so instruction in ID is different from the instruction in write back stage. So actually, this is the ID is not identical to the data of load word. So we need to avoid this, right? How? How? So we need to make the ID of this connected to this write register port as the ID of load word in write back stage. Right? Do you understand? So if we can make this signal as the ID of instruction, the instruction in the write back stage, then we can identify the data and the RD of the instruction. Okay, we can set that we can use the correct RD of this data, so this instruction in the write back. How? So the data is here. Okay, so which means that we can make RD is also here. How? So RD is also RD passed through the pipeline registers until the write back stage, because you know the data is in the write back stage. So which means that the RD of this instruction also should be the write back stage, which means that and if you see that this write to register port here, so as you can see, actually the write to register port of this register file is not connected to the instruction from instruction fetch and ID pipeline register. Right, because and then actually this RD is given to the ID EX pipeline register, right? So which means that in this ID passes through this pipeline register, then this ID becomes the ID of EX stage, right? Do you understand? So this is the ID in ID stage. But if the ID passes through the pipeline register, ID and EX pipeline register, then this RD becomes the RD in EX stage, right? And what is this RD? This is the RD of memory stage RD in memory stage. Why? Because RD passes through the EX and memory pipeline register. How about this RD? This RD is the RD in write back stage. So I mentioned that when the data is written back to the register file, this data is the data in write back, right? And then in order to make the timing of RD identical to the timing of data, then we need to make the RD in write back by passing through the pipeline registers. Do you understand? So if RD passes through this pipeline register, then this RD becomes the RD in EX stage. So RD in EX. So this is the RD in memory, and then this is the RD in write back. So this RD needs to be given to the right port of the RD port of the register file. So by doing this, we set the timing of data identical to the timing of RD. So you need to understand this. This is actually the very important. Okay. So when a certain data is given to the data path element in the pipeline architecture, then we need to consider the timing. We need to use the correct timing of the data. It's very important. Sometimes the students can be confused because, oh, so RD, so actually we need to access the register file. So RD is just connected from the so this pipeline register sometimes. So but when a certain data is consumed or processed, then we need to make the correct timing of the other data or other control signals in the pipeline architecture. So this is very important. So if this timing is incorrect, then our processor will generate the incorrect result. Okay, it's a bug. So we need to set, and then also the same rule can be applied to the control signals. So actually in this figure, I just showed the data path elements, right? So there are no control signals in this figure, but when we design control signal or control unit in the pipeline architecture, then we also need to use we also use the correct timing of data. Okay. So this is some example of the store instruction. Okay. So write back. So actually, the store does not use the write back is not required for the storage, but storage store also consumes the clock cycle of the write back, because in the pipeline architecture, every instruction actually needs to take every stages or every clock cycles in the pipeline architecture. Okay. So actually, so I believe we can easily understand the behavior, how the instructions are executed in the single cycle processor. This is because the one clock cycle is mapped to the execution of one instruction, right? So it's easy to understand the behavior of the single cycle processor. But in the pipeline architecture, actually, one instruction takes 5 cycles until from the instruction fetch to the write back of the instruction, right? So if we just focus on the one instruction, like this is load word actually, then this one instruction occupies 5 cycles. Okay. Instruction fetch, ID, execution, memory, and write back. So actually the instruction on instruction, a single instruction completes each operation after 5 cycles, in 5 cycles, in the pipeline architecture. But at the same time, another instruction is in the different stages. Okay, so that's why sometimes some students are confused. It's a little bit tricky for understanding the timing of instructions in the pipeline architecture. So this is because actually at the same time there are multiple instructions in the pipeline processor, and then these multiple instructions are in the different stages of the pipeline processor. Okay, so we can use this figure like that. So this is the clock cycle, and then this number represents the clock cycle number, and then also we identify the location of instruction. So which means that in the clock cycle number 1, the load instruction is in the instruction fetch stage, and then in the clock cycle number 2, then load instruction is in the ID stage, and then at the same time, the next instruction, sub instruction is in the instruction fetch stage, right? And then the clock cycle number 3, load is in the EX, and then sub is in ID, and then the next instruction add is in instruction fetch. So, and then if you see this CC5, the clock cycle number 5, then we can find that 5 different instructions are in the 5 different stages of the pipeline processor. Do you understand? Okay. Yeah. Oops. Okay. Okay, so sometimes, so we can use the symptom this pipeline diagram like this, and then we can actually simplify the figures. We can use some rectangles to represent the timing of a pipeline process like this. Okay, so and then I frequently use some characters like instruction fetch, ID, execution, memory, and write back. And then regular cycle number 2, and sub is in the instruction fetch, execution, ID, then execution, like this. Okay, so actually you need to understand when a certain instruction is in the which stages of the pipeline architecture. Okay, so you need to understand the exact timing of instructions in the pipeline architecture. So, and then if we just focus on the a certain single cycle period, then we can observe that multiple instructions are in the different stages of pipeline processor like this. Okay. So as you can see, the load is here, sub is here, head is here, load is here, head is here. Okay. So there are different 5 instructions. The 5-stage pipeline architecture. The same clock cycle. Okay. Okay. Then, as I mentioned, we also need to consider the control signals. Okay. So when we design the pipeline architecture, the pipeline processor, then we just focus on the how to connect data path elements, right? Here. Then we need to design control unit. Okay. So like the single cycle processor, the pipeline, the data path elements of the pipeline processor also has the control port. It's actually the same control port. So you can find some control port here, the read write ALU source, the mem to read, and then some ALOP here. Okay? Then how can we connect the control signal, and how can we design control unit in the pipeline processor? Okay? So in the single cycle processor, so we actually think like this. So in the single cycle processor, we have the main control unit and then the ALU control unit, right? And then to the main control unit, instruction. So actually OP code. OP code is given to the main control unit, right? And control signals are generated from the control unit. Then where is the instruction? So where can we know the OP code of the instruction? So in the pipeline architecture, the instruction is fetch the instruction fetch stage. So you can say that, oh, we can know the instruction at this time, but this is the late part. The late part of the instruction fetch stage. So it's too late. So you need to consider that every combinational logic has delay. But so in this figure, so you can get the instruction, but this instruction is generated at the late part of the instruction fetch cycle. So, and then as you can see, this instruction is then pulled by instruction fetch and ID pipeline register. Then we can get the instruction in ID. Okay, just after the rising edge of this instruction fetch and ID pipeline register. So just after the rising edge of the clock at the instruction fetch and ID stage pipeline register. So we can get instruction here. So we can get instruction at the early part of the ID stage. So which means, oh, the control unit can receive OP code. So from the instruction, control unit can receive OP code in the ID stage, right? So as you can see here, the control unit is in the ID stage. Okay, then it's actually the data path is the same. So we just define the control unit in the single cycle processor part. So we define the functional behavior of data path elements, the single cycle processor part, right? So actually the control unit is the same, and then control unit generate the control signals, right? But we need to understand that these control signals are controls signals in ID stage. Right. You understand? So when we discussed about the RD of the load instruction, then I just define the RD in ID, RD in EX, RD in memory, and then RD in write back, right? And then this RD is used in the write back stage, yeah, right? So which means that when the RD is written back to the register file, then we need to use the RD in write back. So, right? So control signal is the same. Control signals are generated in the ID stage. So which means these control signals are control signals in ID. Okay, control signals in ID. But if we see that this figure, so we can find that ALU source is in the EX stage, right? And then how about the mem write? Mem write is in memory stage. So mem read is in memory stage. Mem to read is in write back stage. So what I want to say is that control signals are generated in ID stage. So these are control signals in ID. But when the ALU source control signal is used, then this control signals is to be used when the instruction is in EX stage, right? Do you understand? So what does that mean? So in this case, we need to use the control signal in EX stage. So how can you make the control signal in EX stage? By passing through the pipeline register. Okay. So you can find some control signal. So actually all control signals pass through the IDEX stage, and then we can use these control signals. So it becomes the control signals in EX. And then if some control signals are used in the EX stage, then we need to use these control signals. How about the mem write and mem read? So I mentioned that we use this mem write or mem read signal in memory stage, which means we need to use the control signals in memory stage. How? You can find some control signals here, and then it passes through the EX and memory stage here. So this is the control signals in memory stage. So we need to use this control signal. Write back is the same. So we need to use the control signal in write back by passing through the pipeline register. So do you understand? So if a certain data or certain signals are used in a certain stage, then we need to use the signals in this correct stage. Okay. So for example, if the control signal is used in the EX stage, then we need to use the control signals in EX. So which means that the timing is also needs to be correct. Okay. So if we understand these, then I believe we can understand the behavior of the pipeline architecture. So which means that all signals or all data, so we need to consider the timing of all control signals and then all data signals. Okay? So you can find this is the figure of the pipeline control. So as I mentioned, so this is the main control unit. So control signals are generated by control unit. And if you see the ALU source, then it use the control signal in the EX stage here. Okay. Because ALU source is used in the EX stage. Mem write is the same, and the mem to read is the same. Then, how about the reg write? The reg write is necessary in write back stage, right? Because the register write is done in the write back stage. So, which means, as you can see, here, here, and here. Do you understand? So we use the control in write back for the red one. So I hope so everyone can understand the timing of the signals in the pipeline processor. So I mean it's a little bit tricky because actually the timing is different for the timing can be different for the location of the instruction. But if you see some flow and then the definition of the signals each stage, then I believe I can understand. Okay. Okay, so it's the end of this class. And then any question? Thank you for your attention. And I will post the lecture video for the next class. Okay. 감사합니다.